Good afternoon, everybody. One, thank you for the opportunity. I want to thank D-Wave for allowing me to be here and the partnership. I want to reiterate the excitement that we at Davidson have around being able to host a D-Wave Advantage system in our facility sometime early next year. And what that means to our customers and the things that we are focused on, which I'll hit on some of that here in a minute, really centers on the defense of the U.S. and how these types of innovative technologies can be applied differently to improve those capabilities. We are focused on the adoption of quantum technology. As I mentioned, we believe that it has a future in these types of applications with our customer set, and primarily focused on national defense, homeland security, and just overall national security problems. Our mission is to design and deliver advanced intelligent technology solutions for our customers, and I think this is a great example of how those types of solutions can be applied. We are primarily a engineering services, software solutions company. So we develop mostly simulations, algorithms, tactical software for command and control capabilities, as well as provide subject matter expertise for various problem sets that are critical to the country's defense. And optimization is obviously a part of that capability set. And so that's where we see a significant opportunity, in addition to our applied artificial intelligence and machine learning algorithm development, to leverage these types of technology areas to improve our customers' performance. As Murray mentioned, I'm going to go through two different use cases that we looked at. One is an interceptor assignment problem we call a weapon to target assignment problem. I'll get into exactly what that means here in a minute. And a radar scheduling problem. And again, our focus is on primarily defense applications, but in this case, these are primarily missile defense related applications. That is a core competency in a domain area that Davidson has long been a significant part of and has a significant capability in. With the interceptor assignment problem, the solution scales exponentially. And I'll talk to exactly what the variables are and how they impact the solution here in a minute. We've been working this over the past year and a half, both of these problem sets, and have seen growth and an increase in performance as we've learned how to structure the problem and utilize the D-Wave Advantage system in a much more effective manner. We are using a hybrid solver generally in these cases. We have done work directly on the QPU. I'm not going to go into the details of which is which in the cases of the two studies I'm about to talk about. But we were able to solve problems directly on the QPU, mostly through QBO problem functions, and we ultimately utilize the solver, as I mentioned, for most of the research here. And so these are the two problems that I'm going to spend more time on. I'm going to move to the weapon to target assignment problem, also known as interceptor assignment. So this is a more realistic version of the problem we solved last year at Qubits. If you remember, I did a demonstration of a capability that we developed called Decision One. Had a little bit of a rudimentary component to it from the standpoint of it was less complex of a problem set, even though there were over 60 million possible solutions in particular problem. What we've done is we have advanced the problem to a significant higher level of complexity. And the reason we did that is we wanted really to drive home how impactful a quantum solution can be versus classical, and I'll get into those details here in a minute. Just to quickly summarize the problem set, what we're looking at, this is a classical missile defense problem. You have X number of threats, you have X number of assets with X number of weapon system capabilities, and we have what we call a probability of kill. And this is how we associate with each weapon system its ability to negate a threat. And the idea, obviously, is to have the highest probability of kill that you can get to, which increases the survivability of the assets that you are defending. And again, what we've done is really just added a significant amount of complexity. What you'll see here is a map. What we're really trying to do is optimize the solution, the firing solution of the assets that we have and the interceptors that we have available to utilize to get to the highest P-kill solution across the entire envelope of any given scenario. In these cases, we started off roughly around 20 threats and increased that up to over a couple hundred threats. Again, the complexity of the problem becomes much more significant when you're thinking about, and these are missiles that are moving at a very rapid speed, a couple 100,000 I'm sorry, a couple thousand miles an hour in certain cases, depending on the type of system that it is. And this is a hit-to-kill technology is what we're simulating in this particular environment. So you're thinking about hitting a bullet with a bullet at very high speeds. And so it's a very complex problem set in the classical sense. And when you start to add in the types of threats that might be that you might be dealing with, it continues to increase in complexity, which again, from our perspective, is the value proposition for quantum technology. Is there is a certain point where the complexity of the problem becomes much too difficult for classical solutions to solve, at least at the speed that they need to be solved. And from our perspective, timing matters. In some cases, you're talking about a matter of minutes to deal with these of threat environments. And so you don't have a lot of time as a decision maker or a battle management capability to decide what's the best solution and how do I ensure that I'm protecting the assets I need to protect. So what did we learn? First of all, a couple just upfront statements. One is all this data is notional, and we did that intentionally because it is somewhat of a national security problem set. We're making sure that this is all unclassified. The second is I'm not going to go through all the details of the math. I do want to highlight my technical director, Jameson Venna, who's sitting here up front. If you have any questions about what we've done behind the scenes here that I'm not going to go into those details on, please reach out to Jameson. He'd be happy to walk you through some of the details. But basically, as I described, there's four primary variables here. You've got number of assets, number of threats, the number of actual interceptors with each of those assets, and the probability of kill variability. And again, we did look at different levels of how that gets assigned to each weapon system and the variability of that in the context of the problem set. We utilize an iterative procedure with the hybrid solver to demonstrate the effectiveness of this approach. And what you see here is that with the hybrid solver and D-Wave's quantum technology, we got to a optimal solution, higher optimal solution than the classical algorithm, much faster, and that continued for a period of time. And again, for us, time matters, right? So you can take a classical solution, in this case, with this level of complexity, and it may be a 50% optimal solution versus with the D-Wave system, you're upwards of 90% pretty quickly compared to the number of iterations that we went through. And again, we did a lot of variations on this study. We looked at a lot of different components of what would matter in the context of this particular problem set. And in just about every case, we got similar solutions by using the hybrid solver and the D-Wave system. And again, this was compared against kind of your standard classical solver, in this case, CoinOR, mixed integer program. Let me shift gears for a minute to the other problem set that we looked at, which is a radar scheduling problem. For those of you not familiar with how we use radars in our world, we have what we call phased array radars. They are fixed radar sites with fixed field of views. And they're basically sending out pulses every microseconds, sometimes even faster, between a transmit and receive. The radar sends out a signal. It gets a bounce off of an object, it comes back to the radar, and that way, that's how the radar knows exactly what it's looking at. Now, there's a lot of other variables that I'm not gonna get into the radar technologies here, but fundamentally, that's how they operate. The challenge is they have a limited set of resources. They have a limited set of pulses they can send out in a given period of time. And when you're talking about a lot of objects that a radar has to track, I'll just use space as an example, right? Proliferation of space, and particularly LEO, is just exponentially growing, right? We are getting much more stuff into a infinite AOR, right? Area of responsibility is what we call that. It is the only AOR on Earth today that does not have constraints. It is limitless, right? Space goes forever. So you're talking about a lot of stuff that a particular sensor has to track. And these types of sensors are a critical component to the command, control, and firing solution capabilities for some of the systems that we use to protect both the US and other countries around the world. They are fundamentally, really fundamental to how we track, discriminate, and develop when I say discriminate, what is the object that it's looking at? Is it a big ball of weeds? Is it a an actual missile system. You got to be able to understand what that looks like. And again, there's other variables that come into play there around and the radar pulses at and things like that. But fundamentally, we use these systems in a big way to determine what we can do in a given scenario at a given time. And they enable us to see things that drive a weapon to target solutioning. This is really important. And again, as you're talking about space, things get cluttered very quickly. It's very difficult to understand what's happening. You can't track every object in your field of view. So how do you prioritize and resource and optimize the resourcing of the things that you care about in this context? So again, getting back to search, track, discrimination, it is a focus on understanding what's in, at any given time, the field of view that could be a potential threat, and how does that feed a firing solution that defeats that threat. So it's really important that we understand how to optimize these schedules and these resources. Again, limited resources, you can't look at everything. You need to know what's in, and you need to optimize your schedule for those resources to best track and discriminate the things that matter. And so again, these are pulses that go out in series, and so you got to manage all of that, right? There's a scheduling timeline associated with this, and you cannot overlap those pulses. That's not how these radars work. So what you see here is really the objective for us was to maximize the number of transmit and receive actions that can be scheduled for each resource period. And the resource period can be defined by just a set time limit. I'm not going to go into the details from the study standpoint of exactly what we looked at, but in any given timeline, we had X number of transmit and X number of receive actions that we had to optimize in order to understand exactly what was the most efficient mechanism for these radars to operate the way that they needed to and track the things that they needed. And what we did, these are randomly generated transmit and receive pairs that's representative of that space awareness use case I just talked about. And then we determine the optimal scheduling for those actions. So the constraints included the correct spacing between the transmit and receive actions, which is defined by the expected time the waveform will take to travel to the object and return to the radar. And that actions from any transmit-receive pair cannot overlap on the radar timeline. Again, you're dealing with a lot of things happening in a very short period of time, and it's critical that you're maximizing the efficiency of the resources you do have. Otherwise, you're going to miss something, or you're not going to be able to understand what you're seeing in the context of how the radar interprets the data. So what you see here, just some of the constraints that we looked at. Again, you can't overlap either transmit or receive, or transmit and receive. And so what we came up with, what D-Wave with our application came up with, was the most efficient approach, an optimal approach to managing these transmit and receive resources in a manner that enabled us to validate the correct tracking of the things that were in the field of view. And again, there's more work to be done here around how quantum shows up with this type of use case, but it just gives you, again, an example of the power, I believe, in quantum technology and the applications that we believe have a future as a part of our national defense. What are those future applications? These are just a few that we at Davidson consider to be important to us and our customers. You've heard a lot about materials simulation and material research, so there are specific things that are happening within the United States government that focus on how to utilize materials in an advanced way. We believe that quantum has a role to play in where that goes. Complex logistics, obviously, optimization of logistics and scheduling and how you move things around the most effective way is a critical component to how the Department of Defense and other parts of the logistics community think about getting better, having better solutions, more optimal solutions. We believe quantum will have a significant role to play in the future of the applications that drive these complex logistics and the solutions associated with them. Autonomy. A lot of things happening around autonomy. We talk about there's unmanned air vehicles, there's other autonomous systems that are a part of what we do today relative to operational environments, drones, et cetera. This is the future, right? Unmanned aircraft is the future, and it's here now, but it will continue to grow as the investments are made and the technologies advance. how do you use quantum to optimize the algorithms for what we call collaborative autonomy, which is having things work together in a way that's optimal to either defense of a target or an offensive capability, whatever it might be. But there's a lot of areas where I believe, and our team believes, collaborative autonomy will be a part of quantum solutions in the future. JADC2, this is the Joint All-Domain Command and Control capability that the U.S. government is putting in place across multiple services. This idea of a kill web discovery. So think about multi-domain sensors. I talked about the application of a radar in a very specific missile defense use case. Sensors are critical, not just to missile defense, they're critical to a number of offensive and defensive systems. And then optimizing the shooter pairing, which again gets back to the weapon to target assignment problem. And how do you get the most optimal firing solution against a particular threat? And then overall command and control optimization. We believe that eventually, as we get better at developing the right kinds of applications, as we can make these decisions, most optimal decisions come through more quickly and have the ability to give the warfighter as much data with optimal firing solutions as quickly as possible, that's going to be a part of the equation. But this overarching idea of battle management, command and control, and the optimization of solutions in those environments is something that we believe quantum technology in general is going to be a key part of the future. And then mission planning. This is how you shape tactics, right? Really looking at it from the standpoint of a decision maker. How do I organize my systems to put together the most efficient and effective way to either defend a particular area or in an offensive case, go after an adversary very differently than what we would do today. And so quantum has a role to play there, I believe. And it's really focused on, again, delivering the most optimal solutions to the decision maker as fast as possible. And everything we're talking about, speed is critical. And I believe a lot of these areas, and there's a whole host of others that are out there that we at Davidson in particular are not yet necessarily focused on. Again, I think there's a pretty robust opportunity set for quantum technology to better enable these types of actions. And the more we can enable these types of actions, the less we need them, right? And so that's a critical component of it. It is really about deterrence in the context of supporting the U.S. government and building the best technology available. The idea is if you're ahead of the game, that does deter potential adversaries from even considering aggression. Multiple value propositions to the customers that we support, numerous problems that are still yet to be investigated. A lot of what we've done here today and what I presented here today has been internal research and development activities for Davidson in conjunction with D-Wave. I think there's a whole host of things that we haven't even discovered yet that are going to drive more adoption and better inclusion of these types of technologies and innovations in the future. We have seen, although I highlighted some areas where the quantum solutions show improvement, there's still a lot of similarities with classical solutions. And so it's really figuring out where does the complex problem set that requires the quantum annealer in particular and the hybrid solver to better support. But we think that's going to grow quickly. I think there's going to be a discovery period here over the next 2 to 3 years that drives a number of paradigm shifts in our customer set and leveraging quantum technology as a part of that. And we're going to continue to investigate in this space. Obviously, we're bringing a D-Wave Advantage system to our facility in Huntsville. I think it's a great opportunity for our customers to get better access to the types of capabilities that I've talked about here today, as well as future capabilities that are going to shed the light on how these types of advancements and innovative compute technologies can drive more efficient operations and obviously more optimal solutions for our customers. Thank you for your time. And again, any questions you have, come see me after the fact.